In this example, we're looking at a shaft which is made up of two parts, 1 and 2. 1 is a solid component, outer diameter of 2d, material modulus of g. 2 is a tube, it's got an outer diameter of 2d, also inner diameter of d, a material modulus, shear modulus there of g. We have these torques, the 3t and t, acting at c and d. What we want to know is some information here on the shear stress in the bar where it is at a maximum, and we also want to calculate the twist angles in the connectors. My process is going to be to go through our 4 steps. The first one always is looking at equilibrium. How many equations can we get just from equilibrium? What I'm going to do is draw the free body diagrams of our connectors of C and D, and keeping in mind that between connector C and the wall is member 1. So member 1 is carrying an internal torque there of T1. So we know the equal and opposite on this connector C is torque T1. There's going to be, let's not forget that between C and D there is connector 2. So it's going to be carrying its internal torque there of T2, so we know we have equal and opposite on connector C. And then of course there is the applied torque there of 3T, and then on connector D we have the equal and opposite torque there of T2 with the applied torque of T. So if this is C and this is D, for equilibrium we have for connector C, when we do our moment equation, we get T2 minus T1 plus 3T. For equilibrium that is a 0. For connector D, when I do my moment calculations, I get a minus T2 plus T is equal to a 0. The great thing about this, the problem is determinate. So we can take the second equation and see that T2 is equal to the applied torque T. The first equation then says that T1, which is equal to 3T plus T2, so that's going to be 4T. So this gives us right away, without solving for using any of the other steps, we can get the torques because this problem is determinate. The torques that we have in 1, we have the equation there of torque 1, the radial distance of rho, the second polar area moment there of IP for 1. So IP for 1, that's a solid shaft, so that's equal to 1/2 pi its radius, which is 2d, over 2 to the 4th. So this is 1/2 of pi d to the 4th. Tau 2. That's going to be torque 2, the radial distance rho, divided by IP2. IP2, keep in mind, is a tube, so we take the 1/2 pi 2d divided by 2 to the 4th, and subtract away the material that makes up this whole, so that's 1/2 pi of d over 2 to the 4th. So this becomes 1/2 pi d to the 4th minus the 1 over 2 to the 4th, that's going to be 16, that's 1 over 32 pi d to the 4th, so that will be equal to 15 over 32 pi d to the 4th. So that's going to be the torque distribution. So for the maximum torque, those are calculations for shear stress. The maximum shear stress in element 1 is going to be tau max for 1 is when rho is equal to the outer radius, which is going to be 2d over 2. The maximum shear stress in 2, that's tau max for 2, is going to be on the outer surface of that, which is going to be also when rho is equal to 2d over 2. So we have everything that we need to calculate here. It's asking us to find the maximum shear stress overall. So what we will need to do is compare and take the largest. The largest will be the maximum overall shear stress in that shaft. And those will, of course, depend on our numbers that we get back here for T1 and T2 and our different terms there of IP1 and IP2. For the second part, we're asked to find the twist angles. So we can say that the twist angle for connector C is going to be the rotation there of the wall. So I'll call that delta phi b, that's a 0, plus the tau 1 L1 divided by G IP1. And the connector there at D is going to be equal to the rotation at C plus tau 2 L2 G IP2. So obviously the length for 1 is going to be equal to the distance there of L. The length for 2 is going to be equal to 2L. And we have everything else that we need. We have IP1 and IP2 from before. So these are the rotations of our connectors there for C and D. So in this problem, we were helped out by the fact it was determinate. That simplified things a bit. We were able to solve for the internal torques right away, and then from that we were able to get the shear stresses there of tau 1 and tau 2. We were looking for the maximum. The maximum in each case is going to be in the outer surface of each element, so that's at rho equal to 2d over 2 for each one of those. And then we used our compatibility relationships to find the rotations as we move from the left into the right, and we got expressions there for the rotation angle for C and the rotation angle for connector D.